Welcome to Organic Chemistry in the Morning. I'm your host, Dr. David Irvin. We'll be talking about finishing up Module 3, which is acids and bases, and then we'll probably get into a little bit of the starting of alkanes. And it's more about the conformation of alkanes, not how to name them, because we did that last chapter, but about some of the different properties associated with them. So let me go ahead and start sharing my screen where we are in acids and bases. Okay, because we just finished with solvent effects. So let's go ahead and share my screen. And that's not going to work because it's not plugged in. Let's see, I got to move it once and leave it alone. All right, can everybody see my screen? All right, so I'm going to go ahead and put my gallery mode up over here, so I can see all your bright, shiny faces and the various caffeinated beverages you're drinking. Okay, so okay. I have my thing on. Okay, good. My mic is on. Okay, so this is where we stopped last time. And we said that the acidity also involves solubility. In fact, if you have more interactions available to you, it will be more acidic. If you have a more nonpolar section of your carboxylic acid, it will be less acidic. So that is talking about how a solvent effect can also affect the acidity of a compound. Remember, we have four things that affect our acidity of a compound. We have the nature of the atom, which is the size of the atom and the electronegativity of the atom. We had the delocalization. Oh, no, we're going to do delocalization next. We had the inductive effect. And then we also had a okay, so this is our size and our acidity. Right here, we had our solubility and solvation. And we also have the resonance and delocalization, which we'll talk about now, and then we'll get into the hybridization after that. Okay, so those are the four things. We talked about electronegativity and size. That was a big one. And then that inductive effect, drawing electrons. And then also, do you have a question, Alexis?
No.
Okay. So the inductive effect are withdrawing through those, but that also is tied into that solubility effects, solvation effect. So now we're going to look at the resonance and delocalization of charge and show how that affects acidity, and then look at the hybridization of the atom, looking at what orbital or the size of the orbital and how that affects the acidity here. So let's go back to where I was on the screen. Sorry about the nausea-inducing scrolling here. Okay, so let's talk about delocalization of charge. You can think of this kind of like the idea where we had the size of the ion was more acidic because it could stabilize that charge more because it had a bigger surface area. But now imagine instead of just being a big atom, you're sharing it over multiple atoms. So it's the same thing. You're sharing that charge over a greater area or a greater number of atoms. That leads to a more acidic proton. Okay, so let's do a direct comparison here. We have two things that are very similar here. We have methanol here, and it doesn't have any way to delocalize the charge, and so the negative charge stays on that oxygen. Okay, and so when we look at this, we have a point charge. We have that just that one oxygen stabilizing charge, and our pKa is right around water at about 15.5. Okay, now in acetic acid, remember when we were drawing those Lewis structures of those acetate ions, we had a resonance structure where we could move that negative charge back and forth from each of those oxygens, giving each of those oxygens a partially positive charge and giving each of these bonds a partial one, each of them is a 1.5 bond. Okay, so what that means is we can now spread that charge out over those two atoms, making it more acidic. So do you see how it correlates to that size of the ion being more acidic? The delocalization also makes it more acidic. Does it have to be in the way where we have these going back and forth between two oxygens? Not necessarily. We can do it in other cases as well. Okay, so let's look at a different way to do it. And one of the things we looked at was this hydroxy unit on a benzene ring. This particular thing is called phenol, and we'll learn more about that next semester. But the concept is we can show you that it has resonance structure because of that alternating single double bonds in the ring of the benzene. Okay, so a regular alcohol was at 15.5, acetic acid is at 4.47, but phenol is somewhere in the middle. And the reason it's in the middle is that once we deprotonate our oxygen here, the lone pair can then come into the ring and go rotate around the ring, putting the negative charge on a total of 4 different atoms can stabilize that negative charge, spreading it out over a wide range. Okay, now notice it's not as acidic as the acetic acid, which has it stabilized only over 2 atoms. Okay, turns out that that negative charge on carbon, because it's not very electronegative, doesn't stay there very often. And so it's not as acidic as acetic acid because those 2 oxygens are more electronegative than the carbon, but it still does contribute to the resonance of it. And therefore it is more acidic than a regular alcohol would be. Okay, does that make sense that when we spread that charge out over more area, it becomes more acidic? Okay. So let's look at that based on hybridization. Okay, so in the case of hybridization, the more S character you have, the more spherical the orbital is, the more it can stabilize charge. Okay, so let's think about that. In an sp3 hybridized orbital, we had 3 p's and 1 s. So spread out over those 4 orbitals is that 1 s, meaning it only has 25% s character. Okay, so if the spherical s orbital can stabilize that negative charge better, we only have about 25% s. Okay, so let's look at an sp2. Okay, so we have a total of 3 equal orbitals. We have 1 s and 2 p's, and we're spreading that s out over those 3 orbitals. So that's about 33% s. So just by that argument there, the sp3 hybridized hydrogen should be less acidic than the sp2 hybridized hydrogen because of that less of an S character. So let's go to that last type of hybridization we have in carbon, which is the sp. That means it's half S, half P, and it should be able to stabilize the charge even more, making it more acidic. Okay, so let's look at the pKa values. Okay, so if we look at this, wow, it's a trimethyl. It's a trimethyl compound with this acidic proton here. So we're looking at pulling that hydrogen off there. And this pKa is greater than 70. I think that might have something to do with the solvation effect from that large group of methyl groups there. So usually alkanes are 50 to 70 right here. So our inability of that S to stabilize that charge makes it less acidic, and it has a higher pKa value. Okay, so just by increasing it from 25% to 35%, we've dropped the pKa down to 44, making it more acidic. Okay, and when we increase it to that 50% character, we end up with the most acidic hydrocarbon hydrogen. Okay, so it has everything to do with stabilization, and it has everything to do with having more and more of that S character in it. So that gives us our nice trend on all of the different hydrocarbons, from alkynes to alkenes to alkanes. Okay, questions on hybridization versus acid strength? Okay, the other thing I want to note here is that notice that that orbital in each of those cases has 2 electrons in it. Now remember, when we take away a hydrogen, both of the electrons from that sigma bond stay behind on the parent molecule. So that orbital does have 2 electrons in it. Okay, there we go. Okay, So let's look at that as compared with other um, atoms that we have. If we look at the size of the orbital for this, they are going to have different, um, the different atoms and the different orbitals have different sizes, right? So we're going to compare the different types of anions, carbon versus nitrogen anions, and which atom will better stabilize the negative charge. That is also makes it the weaker base or more acidic, right? So let's look at the different sizes here. And if we looked at the series between the alkane hydrogen, the alkene hydrogen, and then we have ammonia there in the middle somewhere, and then the alkynyl hydrogen, if we compare the size of those different hybridized orbitals, what we'll see here is in nitrogen, the size of that sp3 orbital is actually between the size of an sp2 orbital and an sp orbital. What that means is that its acidity should fall in between the alkene and the alkyne. And when we look at the series here, we have again our alkanes very high, 55 to 70, our alkenes right around 44. Our ammonia is right here in the middle at 38, where our acetylene is 25, 26, which is our most acidic hydrocarbon. So that orbital size, that hybridization leading to the orbital size is driving the acidity, or in this case, the basicity. So the basicity of the conjugate base right here. So this is going to be the most acidic, the most basic, the next most basic, and going down, because this is the least acidic, making this the most basic. Okay, so do we see that hybridization has an effect on that? And so when you look at the table of all the different types of things we have, you can actually start to see some correlations on types of atoms that stabilize charge. Like oxygens are really more acidic, then we have nitrogen compounds, and then we have the hydrocarbon compounds. And we can draw analogies to the different types of hybridization as well. And the other rules of electronegativity, dissipating charge, and ion size. All right, questions on that hybridization? Okay, so now we've talked about pKa's, and we're going to use mostly pKa's in this until we talk about amines. I'm going to talk about amines today. But then we can also talk about it from the other's point of view, which is the pKb. The pKb is the base constant, or the log of the base constant. So we're looking for that deprotonated species in the system. It doesn't have to be hydroxide, but it can be. So let's look at that. And we want to say that, first of all, strong bases are unstable and very reactive. Okay. Now, the reason they're unstable and very reactive, I'll talk about in a minute, but the weak bases tend to be more stable and non-reactive. Okay, so when we're looking at something in our system that was a very weak acid, when we turn it into a base, it's going to be really reactive and really unstable. We just can't keep it around. It'll react with air, it'll react with water. The weak bases like chloride ion and iodine ion would be very weak bases because they were strong acids, and they're very stable and non-reactive. They'll just sit around and be an ion and be happy with it. Okay, so let's look at that. Excuse me. Must be a little high on mold count today. Okay, so let's compare the case. In this case, we have a reaction where we're comparing the amide ion, or the ammonia has one proton removed, and we're going to compare the pKb's and the pKa's of the species available to us. Okay, so in this case right here, this is our base right here, and this is our acid because it's going to donate the proton to the base. Okay, which means on the opposite side, this is our conjugate acid, and this is now our conjugate base. Remember, when we see where the equilibrium lies in this reaction, we always look at either the pKa of the two acids or the pKb of the two acids. And so we should be able to get the same answer for both. So let's look at the pKb, since we're talking about base strength. The pKb of this is -22. Okay, So remember, the lower the number, the more it is. In this case, we're talking about pKb, so we're talking about base strength. So that makes it a very strong base. It's a negative 22, very strong base. Okay. If we look at the pKb of the conjugate base, it only has a pKb of minus 1.7, which means it's not as basic. So it is a weaker base than this right here. Notice it's a strong base because it's negative. Okay, it's a very strong base. It wants to completely dissociate. However, it's a weaker base than the one on this side. Therefore, it's going to shift the equilibrium toward the weaker base. Okay. Notice that if we compare the pKa's, we actually see the same thing. We're going from this stronger acid to the weaker acid in the system. But I want to compare just base strength for the next few slides. Okay, so we're going to talk about more about that pKb. Okay, so I said that strong bases are unstable and very reactive, right? Well, let's look at a weak base here. I said the halide ions are kind of weak. If we look at the pKb of this chloride ion, it's 21. So it's very positive, and therefore it should be fairly weak compared to those other two bases in the other example. If we take our base and compare it to our conjugate base over here, and we see that the hydroxide here has a pKb of minus 1.7, just like above, right? Okay, that means the hydroxide ion is more basic than the chloride ion and means that it's going to shift the other way. It would rather be water and chloride ion than HCl and hydroxide. Okay. And again, we're only comparing one or the other, either the pKa or the pKb. But I want to do base strength for the next few slides. Questions on base strength? Okay. All right. So let's look at that table again, but instead of looking at that pKa side, let's look at the pKb side. Okay. So if we look here, our least acidic compound right here is now one of our most basic, negative 36. Okay, that's extremely negative. That's a very low number, making a very strong base. Okay, and so our hydrocarbons right here, our acetylene ion, our ethylene ion, and our alkane ion here are all very strong bases, which means once we make those anions, those are going to be very reactive species. Another very strong base we're going to use a lot right here is this amide ion here. It's a nitrogen with two hydrogens and a negative charge. It's a very strong base. In fact, notice this is a stronger base than this, meaning that we can make this acetyl from this base. Okay, but because this is more basic than that, we can't make that ion from the amide. So just like in acidity, you can't have it the stronger, it always moves toward the weaker base. We cannot use a weaker base to make a stronger base. Okay, so let's look at a couple other important ones that we're going to use a lot. We're going to, well, you'll use that next semester, but let's look at this one right here. This is kind of weird. This is an alcohol, but it's one of these ones with a whole bunch of, it's really fluffy. That has a base strength of -4. So it's less acidic than the regular straight chain alcohol, but it's more basic. So this right here is what we call T-butoxide, and T-butyl alcohol that we're going to remove an ion on, and we're going to use this as a base in a lot of reactions. And I want to show you that we use it because, number one, it's a stronger base than other alcohols, and we'll be able to see that. And then we got hydroxide right here at the cusp. And then notice all of these are now positive, okay? All of those are now positive, so they are considered weak bases, okay? And so we have that alkoxide ion is a 4. This acetate is a 9.2. And then if we go up over here, we get all the way down to where we have water, which has a pKb of 15.7. Okay, And we have the bromide ion is way up here at 23. Okay, so now just using that pKa to pKb comparison, the very strong acids become very weak bases become very strong acids. All right. So there we go. Now I've used both sides of that chart. So let's talk about a little bit of a special thing called the amine base strength. Okay, I said we weren't going to talk about pKbs except when we talked about amines. And this is important because the way the equilibrium lies in amines has everything to do with the pKb, not necessarily the pKa. Okay, so what we're going to look at is this equilibrium of this amine with water, but it depends on the stability of the conjugate acid. Okay, so how stable is that conjugate acid will direct how far it goes back and forth. In order for the amine to be a strong base, its conjugate acid, the cation, must be stabilized such that the equilibrium is shifted to the right. Okay, boy, I could have said that differently. Anyway, so that means that anything we can do on that nitrogen to stabilize that positive charge means it's going to make it more stable. And therefore, we need to think about things that are going to either donate electron density or remove electron density. So we need to think about how we can add or subtract electron density from that nitrogen to encourage that conjugate acid to be more stable. But always remember, amines are weak bases, and there are many stronger bases that we can use to do this. Okay. Okay. So let's talk about one of the effects that can help stabilize that charge would be resonance. Okay. So in the case of this, I have a series of amines. And in this case here, we have an aromatic amine. We have an amine on a benzene ring. And we can think of this benzene ring as fairly electron rich. But we also have the chlorine, which is a high electronegativity atom and would pull electron density away from the benzene ring. We now have a nitro group here. That's also, we learned, is a very strong inductive effect on the system. Then we have our amine with just the benzene ring, so we can look at that as our baseline. And then we have an amine where we have just aliphatic hydrogens nearby, okay, aliphatic carbons nearby. So there's no effect, there's no way to make it stabilized. Okay, so if stabilizing the positive charge increases the basicity, that means that we need something that's going to pull electron density away to make that positive charge less positive. So in this series, our strongest electron withdrawer here is our nitro group here. And notice our pKb is at 13, okay? So that is our weakest base. Okay, because this electron withdrawing group is pulling electron density away from the side, it's making our positive charge that forms with our conjugate acid more stable, making it a weaker base. Now, let's look at if we don't have that nitro group here, it's down here. But if we have this chloride, which is a moderate electron withdrawing group, it does increase. It becomes less basic. Okay. But if we do not have any of those effects at all, we cannot stabilize that charge. It becomes more basic. So aliphatic amines are always more basic than aromatic amines because of those available electrons to come here and inductively affect the name. Okay. So we kind of have to think of it backwards like that, but it's all about the conjugate base and conjugate acid stability. All right, so let's look at that again with the effect of hybridization. We saw before that a hybridization helps with the more S character, the more stable it is, okay? So in the case of our nitrogen hybridization here, our nitrogen here is sp hybridized, and therefore it should have a decent acidity if it had a hydrogen on there, but it doesn't have one. It has a lone pair. So that means it can't act as an acid, so it has to act as a base. And we see the pKb of that is 24 right here. So that means that it is a fairly weak base. However, once we go to that, we actually can protonate that lone pair here, and then that has a pKa of -10. So what does that mean? That means this is a very strong acid right here. So I believe that because of that, the equilibrium is going to lie in that direction here, because that's a super strong acid. That's a super weak base. It's going to go back to the other side. And also, this is a fairly strong base as well. This has a pKb of -1.7. So we're making a really strong base and a really strong acid if we do this reaction. But it has everything to do with the idea that we actually have those lone pair on nitrogen is what's accepting the proton. Okay, this lone pair on nitrogen is what accepts the proton on all of its acid-base reactions. Okay, so let's look at another couple ways where we're looking at different types of lone pairs. Okay, in the case of this aromatic amine we have here, it's just like benzene ring where we have alternating single and double bonds, which means the nitrogen has to be sp2 hybridized so that it can have a p orbital to donate to the ring here. Okay, so if that's sp2 hybridized, that makes these hydrogens sp2 hybridized. Remember, they're sp up here in the first example. These are sp2. Now let's take a different one where we only have aliphatics and we have an sp3 hybridized right here. Okay, so if we look at its ability to react with water here, when we have our pKb is more basic, right? It's still a weak base, but it's more basic. Our conjugate acid is a weaker acid than in the previous case here. Okay, so that stronger base is making the weaker conjugate acid. And this is directly due to this hybridization of that sp2. In the case of our sp3 hydrogen, our basicity is even higher. It's a stronger base than the other two. It's still, they're all weak bases, but, and its pKa of the other thing is also a weak acid. Okay, notice the acid strength is decreasing as our hybridization changes, and our base strength is increasing as our hybridization changes. I'm sorry, our base strength is increasing as our hybridization changes. Okay, so in our hybridization of acids, sp2 is most acidic, sp is most acidic, sp2 is in the middle, and sp3 is the least acidic. In this case, our sp is the least basic, our sp2 is our intermediate, and our sp3 is our most basic. So see how those complete, equal and opposite in our trending agrees with our hybridization as well. Okay, do we understand this? Okay. All right, so let's continue on with some amines and look at the inductive effect. Just like acids, inductive effect plays a role. And when we have things that can donate electron density or withdraw electron density, that should change the acidity, or I'm sorry, the basicity of the different materials. And in all of these cases, we're looking at these electrons here, and those electrons are going to be those sp2, which are intermediate basicity. And we start with our baseline, and our pKb is about 8.75. And so how can we change it? If we wanted to make it go up, we would probably add something to it that removes electron density, making that positive charge less stable. So by having an electron withdrawing group on here, the chlorine here, the pKb goes up, making it a weaker base. In the case of adding these two methyl groups here, those can weakly donate to the system here, and it increases the basicity. The pKb goes down, and the basicity goes up. And let's look at what we see in the trend in our pKa's of the conjugate acid. Right here, our conjugate acid here is about a 5.28. But because of the removal of this electron density here, that makes our conjugate acid 2.8. It's more acidic. It's less stable to have that ion there. And when we look at the other one here, because of our stabilizing effect of having those carbons there to donate the electron density, help stabilize that positive charge, we end up with the higher pKa, the more acidic compound. Okay, so when we see these trends, we can look at the inductive effect. If it withdraws electron density, it decreases the basicity. If it adds electron density to stabilize that positive charge, it increases basicity. Okay, so kind of like that thing where we were adding halogens to carboxylic acids by that inductive effect. All right, so there's also a solvent effect on there, and it has to do with what it can and cannot interact with. The more interactions it has with the solvent to help stabilize the charge, the more basic it will be. Okay, so if we look at this one first, right here, we have a dimethylamine right here, and it's in solution, and it's hydrogen bonding to water. And so we have these two methyl groups. So these two methyl groups are, let me do it a different color. These two methyl groups are taking up some space. So we're not getting any interaction with the nitrogen lone pair on this side of the reaction. We only see interactions with the nitrogen on this side of the system. Okay, so that's going to make it more basic than if we didn't have that interaction. Okay, so once we protonate that, we now have a protonated species, and now the oxygens are actually doing the bonding to our system here. And again, our oxygens that are interacting are only on this side of the molecule. The ones that, all of the stuff over here doesn't interact to help stabilize the charge. So it's only those 5 or 6 molecules of water that can stabilize that charge. Let's put another methyl group on here. When we put another methyl group on here, we take up more zone that it can't interact with. And we're only looking at 1, 2, maybe 3 water molecules that are interacting with our free amine. And then once we protonate it, we again can only get 1 oxygen in here to stabilize that positive charge, maybe a little hydrogen bond here, because more of the molecule is blocked out. So here we only have 1 oxygen stabilizing our positive charge. Over here, we have 2 oxygens stabilizing our positive charge. And therefore, the one with only 1 oxygen should be less basic. And when we look at the pKb's, the pKb for the first one is 3.27 with that good solvent shell, extra oxygen stabilizing that positive charge. And it's 4.9 for the one that has less interaction with the solvent. So it's less basic. So that's analogous to what we saw in the carboxylic acids as well. Okay. Now, a solvent can also affect with electron donation or electron donation in the solvent effect as well. And you saw that in the previous slide, it was all about how much area those groups were taking up, the methyl groups were taking up, okay? So we actually should see a difference if we have a linear system versus a cyclic system. Because we have these big arms here that can flop around and take up space right here, these arms are going to be rotating around and taking up space. They're going to take up more volume than if we pin them back and held them in one position, so that now we have more area here. Because these can flop around more, we can only have interaction on this zone here. Because these are tied back right here, and we'll have more interaction with amine electrons to act as a base. Therefore, it's going to be more basic. Okay, so everything about how much solvent or how much stuff can interact with that that amine nitrogen and that lone pair increases the basicity of the system. So when we have a smaller group, we have an increased basicity. All right. So we talked about amines that were aliphatic that had no thing. And then we talked about amines that had that benzene ring attached to them. Well, we can also do it on the nitrogen attached to that carbonyl, that amide nitrogen, okay? But they're not as acidic as, they're not as basic as other amines because of a conjugation effect and the acidity of the thing produced, okay? So let's look at that and compare. So when we have our aliphatic hydrogen, remember this is an sp3, so it's one of the more basic amines, has a pKa of about 3. When we protonate it right here, it has a pKa of 11, which makes it a weak acid, okay? And so we can make this in a little bit in solution. Okay, once we get to the aromatic system, because of the resonance delocalization, we can move that charge around and give it so that our pK, the pKa of our product here is actually intermediate. It's probably going to be somewhere around 5 or 6. But when we have that amide, the pKb of the amide is actually 13.39, which is a very weak base. And it's also, once we protonate it, it becomes a very acidic compound. Okay, so we're going from a weak base to a strong acid. So there is a possibility to do this, but notice the proton isn't on the nitrogen. The proton ends up going to the oxygen to stabilize that charge. There's still a positive charge on that nitrogen, but the oxygen is the part that gets protonated. So that's why they are much lower basicity than the other nitrogen-containing compounds. Okay. All right. So some of the things that affect the basicity of things is also that same thing that affects acidity. Atom, the atom the charge is on. So we want to have that proton onto the atom that can stabilize that charge more. That's why most of these amines, the amines are the basicities that we were looking at. But also if you have a negative charge on something like a negative charge on a carbon, it doesn't want to have that negative charge. And so it's going to be a very strong base. It's going to react very quickly. Okay. We also had resonance effects. We can see in the system where anytime you can spread charge out, it becomes more basic. We have an induction effect. If you have something that can withdraw electron density, it will increase the basicity of the system. And just like before, the orbital or hybridization also affects our system as well. So the more S character, the higher the base strength. I'm sorry, the lower the base strength. The less S character, the higher the base strength. And also notice it was also orbital size. The sp3 orbital on a nitrogen is actually smaller than the sp2 orbital on a carbon. And so we can see that size does also affect things. All right, questions on acids and bases. Okay. Everybody?
I'm sorry. So the more you say it again, the more S character means more acidic or more basic?
Okay, the more S character, the more acidic, and therefore the less basic. And think of it this way, if we look at acetylene is more acidic than the alkane, like just ethylene, but the ethylene anion is much more basic than the acetylene anion, okay? So the acetylene is sp hybridized, it has half S character, it's more acidic, which makes it less basic than an sp3 hybridized ethyl group. which is less acidic, but much more basic. Okay?
Thank you.
All right, I think that's my last slide on this one. All right, so any other questions on acids and bases? Again, the most important thing is that, you know, strong acid, weak base, you want to look for either the conjugate acid and compare it to the acid, or the conjugate base and compare it to the base, to figure out which way the equilibrium lies. And there are a few of those things you need to take a look at to see what they are. All right, so everybody kind of grab a beverage, take a drink. We're going to transfer over to Module 4, alkanes. So my green tea mug has a whole bunch of chemical symbols on there. I got it free from Thermo Fisher, so I thought it was cool. All right, so let's go ahead and start with alkanes and cycloalkanes. Okay, so acyclic are alkanes that are straight chains that don't have any rings, and then cyclos have those rings. And we're going to talk specifically about cyclohexanes, because cyclohexanes give us an opportunity to look for stereochemistry and stability and some other things we don't see in the other systems. And so we're going to look at those specifically. Okay, so the first thing we need to know is that when we have chains that are hydrocarbons that are straight and we have no double bonds, those sigma bonds undergo rotation. Okay, there's very little energy difference between rotating these around, and we'll talk about that energy barrier there. And therefore, when you have just molecules in room temperature, there's enough energy just in the heat in the room to allow these things to rotate around completely. Okay, so what does that mean? So if I drew the compound on the right and I drew the compound on the left, which one's right? Which one's the correct way to draw it? Well, it doesn't matter, because we have free rotation around each of these bonds. We have a free rotation around this bond. So we could actually end up with this over here, and there's a bunch of different ways that these can be. So what we call these different possibilities, where we haven't broken any bonds, all we've done is rotate them, is we call them different conformers or rotamers, which is changing the shape of the molecule without breaking any bonds, just by rotating around single bonds. So all conformers are possible structures. So you could draw it 100 different ways and they'll probably all be right. And you'll probably be able to find them if you looked at each individual molecule in a solution. You'll probably find each of those conformations at some point in time. Okay, so because there's so many different little possibilities, there are going to be some favored ones. So we have to do what we call a conformational analysis to study the difference in energies going through different rotations. And we'll start to see that certain configurations are more stable or more likely because of the lower energy barriers. And some things are going to be less likely because of higher energy barriers. Okay, so let's start with something simple. Let's start with this ethylene right here. So we only have sp3 carbons, we have tetrahedral shape, and we want to get an idea of how to get our 3D mined onto 2D paper. So let's start with this one right here. And in this case here, lines that are just lines are assumed to be in the plane of the page of either the paper or the laptop here, okay? Now, wedges, solid wedges, are sticking out of the plane at us. So you're going to get poked in the eye with those hydrogens. And then the green ones are actually the dashed line, the dashed wedges stick into the page. So see how just by doing this, we can actually emulate a 3D structure with just a two-dimensional drawing, okay? So let me look at this again using this tool right here. So this right here is all in the plane of the paper, and our hydrogens are sticking up out at us, and these other two hydrogens are behind. So I'm going to do them a little bit smaller, okay? So let's take that structure and rotate it about 45 degrees and look at it again, okay? So if we do that, what we see is that we have our hydrogens that were in the plane of the paper now tilted about 25 degrees out, And we see that this hydrogen is opposite that hydrogen. And in this case, this hydrogen is opposite that hydrogen, and our other two hydrogens are still sticking kind of out toward us, but they're kind of on that same side. Let's rotate it another 45 degrees and draw a new thing called a Newman projection. In a Newman projection, we're able to draw the conformation of the substituents on two carbon atoms, and we can do it without ambiguity by drawing the thing correctly. So in the case of a Newman projection, what we're going to do is we're going to take any carbon chain and say, I'm going to look down just two carbons and see where the substituents are. So that's what we're doing here. We're actually taking our, basically looking like we are going to look down this axis of these two carbons right here. And this is a little I. Oh, that's not I. So this is my interpretation of, we're going to look down that axis, and what we see, the first carbon here, this is our first carbon here, is the one where the three lines meet, okay? So when our three lines meet here, this is the carbon that is closest to our eye, okay? Now, because that carbon is taking up space there, we're going to draw a ring for the second carbon. That second carbon, these little hydrogens are poking out from behind the first carbon here, and that's why we have that structure here. So do we see how the structure is? The three lines coming together is the first carbon we see. The three lines on the ring are the second carbon attached to the first carbon. Okay. So this is what we call a Newman projection, and that allows us to see how close the different substituents are when we start to rotate around this axis. Right here, when we start to rotate things around this axis, what we're going to end up doing is just spinning these hydrogens around and look at their interactions with their neighbors. Okay, so does everybody see how to go from a two-dimensional image to this three-dimensional, but then convert the whole thing to a Newman projection to allow us to get to our ability to watch the bond rotate and see how it affects the energies. Okay, so let's go ahead and talk about some different things. Okay, so by definition, dihedral angle is the angle between four atoms. Okay, so we're looking at a total of four atoms, and in this case, we're going to do this atom, and this atom. So the dihedral angle is going to be the difference that these two hydrogens have if they were in this, if we drew this hydrogen here, this is the dihedral angle of those two hydrogens. And notice in this case here, it's 60 degrees. Okay, so if you can imagine it, if you're just looking down the two carbons disappear and we can only see to the two hydrogens, and that angle is 60 degrees. Okay, so when we have this conformation, we have what we call the staggered conformation. And the reason we call it the staggered conformation is that all of the substituents are evenly spaced around each other. And turns out this is going to be our lowest energy possibility because nothing is butting up against anything else. Okay, so in our case of our Newman projection, when they're all equally spaced out like a propeller, this is what we call our staggered conformation. And we have a dihedral angle of 60 degrees. Now, if we did it by our wedge and dash here, see how this hydrogen actually is sticking out, and this is in the plane of the board, and then this one's sticking out here. So this is this hydrogen, and this is this hydrogen, and that is that hydrogen. So we can see by the going from a stick to a wedge, that's just slightly out of plane, but it's much easier to see on the Newman projection that it's that 60-degree dihedral angle. So I'm going to use that Newman projection to look at these different conformations available to us in these alkanes. Okay, so we saw that the first conformation we had where they were all evenly spaced is called the staggered conformation, and that has a 60-degree dihedral angle. However, if we rotated the red hydrogen 60 degrees counterclockwise, they would start to have a dihedral angle of 0. Those hydrogens are going to be in line with each other. Okay, so all we have to do is rotate that 60 degrees to get this eclipsed conformation. The eclipsed conformation has the 0 dihedral angle. Okay, and so it takes energy to do this. Okay, and we'll talk about that on the next slide. And then we can also do it in the dashed and wedge approach. However, the Newman projection here is going to be the easiest to identify. Okay, so we have two things that we are looking at. We have eclipsed and we have staggered. And the staggered is more stable because all the bonds are as far apart as possible. All the electrons that are on the different hydrogens are as far apart as possible. And there's the least amount of electron repulsion available to us. However, when we have them closer together, we now have electron repulsion between the two hydrogens that are lined up, and we have a change in energy. At room temperature, 99% of this molecule would be staggered, but we would be able to, by increasing the temperature, increase that possibility of having that less stable eclipsed area. Now, why do we say that it is takes more energy? Okay, let's look at that on the side here. So as we come to, if we start in our staggered position here with our two things away from each other, and we move them closer together like this, what happens is they spread out. They spread out. This is called torsional strain because these two hydrogens are now electronically starting to butt up against each other. And each of those hydrogens, it takes 4 kilojoules per mole for each of them, meaning that we have three sets of hydrogens. So the total energy difference between it is 12 kilojoules per mole. Just the one hydrogen-hydrogen reaction is 4, but we have 3 of them. So the total energy required is 12 kilojoules per mole. So we have to have enough heat in our system to allow for this energy difference to occur. Okay, so let's follow it rotating around and see what it does, okay? So what we're going to start with is we're going to look at the blue and the red hydrogens specifically, right here. And we're going to start somewhere. So we're going to start with a staggered conformation with a dihedral angle of 90 degrees, 60 degrees. And then what we're going to do is we're going to rotate that red hydrogen counterclockwise until we get to this conformation, our first eclipse conformation. And notice that change in potential energy. We went from the lowest possible potential energy to a high point, a high potential energy. Now, if we keep rotating that hydrogen counterclockwise, we're going to get to the next staggered conformation and the energy drops again. And if we keep rotating that hydrogen, we're going to get to another eclipse state, rotate it some more, another staggered state, rotate it some more, another eclipse state, until we're finally back at the beginning. Okay, so this is going all the way around, rotating that one methyl group all the way around the other, showing that we have a change in that potential energy as we do it. Okay, staggered is always lowest in energy, eclipsed is always higher in energy. And that's just with hydrogens. What if we change the group so we have something other than hydrogen? Most things are bigger than hydrogen, and so we should see a different effect when we have other substituents. Okay, so let's go up from our simple thing of our ethane. We only had 2 carbons, so we had to look down that bond. In the case of butane, we're going to look down the bond between these 2 carbons here, meaning we're going to have a methyl group on one side and a methyl group on the other side to look at their how they interact with each other and how that steric interaction and that energy barrier changed from just having hydrogen. Okay, so again, what we're going to do is if we drew out our butane here, we're going to look down this axis here. So when we draw our Newman projection, we're going to have a methyl group attached to 2 hydrogens. And then we're going to have our back carbon here. And then we're going to have 2 hydrogens and our methyl group. Okay. So we're looking again down carbon 2 and carbon 3. Carbon 1 is here in the front. Carbon 4 is here in the back. Okay. So that's our Newman projection for our butane. So let's look at that. When we first started here, we're probably going to look at, let's just start it with the 2 methyl groups as far apart as possible. If we have the dihedral angle between the 2 methyls, it's now 180 degrees. But it's what we call the staggered conformation because it looks like the staggered conformation we had before. However, the 2 methyl groups are completely opposite each other. So we call this the anti-configuration. Okay, so the 2 methyl groups are as far apart as possible, the anti-configuration. And it's also a staggered configuration. And I'm going to argue why it's going to be the most stable when we start looking at the energy diagram. If we rotate 60 degrees, we end up starting to get the 2 methyl groups are getting closer to each other. We have them at 120 degrees, but we have a methyl group eclipsed with a hydrogen. We have a methyl group eclipsed with a hydrogen, and we have 2 hydrogens eclipsed there. Okay, so when we had 3 eclipsed hydrogens, we had a 12 kilojoules per mole. With the methyl group and the butting up against a hydrogen, we now have an increased energy required. We have a 16 kilojoules more energy required than our first starting point, which is our relative energy of 0. If we rotate 60 more degrees, we get back to a staggered conformation. However, our methyl groups are now fairly close to each other. We have a name for this. This is called gauche. Gauche is when the 2 larger groups are have a 60-degree angle between. They're staggered, but they're not anti. And there's a penalty for that because those 2 methyl groups are bigger than hydrogens, and you will see them in show up. And so we have this energy barrier is this 3.8 kilojoules per mole, less stable than the anti-configuration. Now, if we rotate it one more time, now we're getting in the worst condition possible. We have 2 methyl groups butting up against each other. We have 2 hydrogens butting up against each other, and we have 2 hydrogens butting up against each other. That's a total energy cost of 19 kilojoules per mole. And so it is much less stable than that original configuration. Okay, and so what we're seeing here is in this, we're going from what we consider the most stable is having the 2 largest groups opposite each other, 180 degrees apart. And then we can go through a new configuration. We had staggered, we had eclipsed, and now we have gauche. Gauche is where our 2 largest groups are 60 degrees apart in our staggered configuration. So what does that look like energy-wise? Well, let's look at that energy-wise right here. And you have to think that each of the interactions between the different groups is additive, okay? So we have very little interaction between any of these because we're in their full staggered position, and we end up with our relative potential energy of 0, okay? So when we move up here, now we have a hydrogen-methyl interaction, which is 6 kilojoules per mole, a hydrogen-methyl interaction, which is 6 kilojoules per mole, and a hydrogen-hydrogen interaction, which is 4 kilojoules a mole, bringing us up to a total of 16 kilojoules per mole, okay? But it could be worse. Those 2 methyl groups could be next to each other. So let's go ahead and continue to rotate counterclockwise, and we get down so that we don't have that interaction with the eclipsed part here, but we do have these 2 that are near each other. They're starting to sense each other through space, and they're starting to pull apart a little bit, giving us that extra little torsional angle, which is that extra little 3.8 kilojoules per mole energy penalty. Okay. Now, when we go up to our eclipsed where the 2 methyl groups are next to each other, that's costing us 11 kilojoules per mole of energy. And then we have, of course, 4 and 4 for our 2 smaller ones, giving us a total of 19. And again, rotating 60 degrees more, getting us to this gauche position here. Okay, notice that this was a gauche position with the methyl group on the left side, and this is now a gauche position with the methyl group on the right side. And that's just because we're doing that rotation 60 degrees. We have that same energy penalty. When we go through our eclipse state, we jump back up, and then we come back down to our anti-configuration. Our methyl groups are 180 degrees apart. That's our anti-configuration. Okay. Do we see how those, which interactions are leading to the most energy, the barrier? The bigger the groups that are in the eclipsed condition is going to have the highest penalty on our energy and going to be the most resistant to go back and forth. So we were just continuously rotating around. Well, what might happen is they might come up to that and just go back the other way because of that energy barrier. Okay. So in like all these, the staggered conformations are always lower, eclipsed are always higher, and Gauss are somewhere in between. Okay. All right, questions on that Newman projection of the butane. So we see that our carbon 1 is where it is, and our carbon 2 and 3 are we're looking down the line, right? Okay. All right. So when we have cycloalkanes, we have a problem. Because they are locked in space, they can't freely rotate. They can flip back and forth, but we can't have full rotation around that sigma bond, okay? And because of the size, some of them cannot be that desired 109.5 degrees because of the size of the ring. So we have to look at things as if they had, that they're being restricted. And so we have to think about that as, okay, how do we know how much energy it costs the molecule to have a smaller or bigger ring? Well, it turns out we can demonstrate this experimentally by doing the heat of combustion of each compound. Basically, we see how much heat is given off. The more heat given off, the more potential energy it had. So the less heat it gives off, the less potential energy it has. Okay, so let's look at this. If we just do a combustion of two different molecules, both having the same molecular weight, the same number of carbons, here we're doing a linear butane, and here we're doing a branched butane here. When we do this, we see a total energy release of negative 2,877, I believe that's joules right there. So that total change in heat, that total given off is that much. However, when we have that branch right here, we have less potential energy because less heat is given off. So we have a lower number here, less heat is given off. Since the butane liberates more heat than the isomer here, it must contain more potential energy. Okay, so if it contains more potential energy, that means this one has less potential energy and therefore must be more stable. Okay, so what we're looking for is the less heat given off during a system, the more stable the starting material will be. Okay, so get that in your head real quick. The less heat given off, the more stable it must have been. Okay, so let's do some comparisons. We're going to look at different cycloalkanes, look at the heat given off, and then figure out the reason it gives off more or less heat has to do with the strain of the ring, the energy required to make that ring and hold that ring in place. So if we look at a ring size of 3, that's a very small ring. Those are 60-degree angles. We're really torturing those sp3 hybridized carbons by trying to make our 109.5 degrees into 3 degrees. So when we combust that and then account for the fact of the number of CH3, the number of carbons in it, so we're comparing apples to apples, the number of carbons right here, we can see that that 3-membered ring has a ring strain of 115 kilojoules per mole. So that 3-membered ring is very strained and has a very high energy associated with it. Now, if we move up to 4, we've now gone to a 90-degree angle. So that's closer than 109 that we're looking for, but it's still not perfect. It's still strained. And when we account for the heat loss and the number of carbons we have, we see 109 kilojoules per calorie ring strain. So we've released some ring strain by going one more carbon, but we're not relaxed like a regular alkane. So let's go up one more carbon. 5, that's getting pretty close. So the 5 is going to be like 120 degrees, right? Okay, well, it's not 109. So there is some ring strain associated with it. And it gets to our 27 kilojoules per mole of ring strain. Now, once we get to our cycloalkanes, remember, we can do a chair in a boat position in this. We can flip around so that there's a little bit of flexibility. So each and every carbon can be 109.5 degrees. Because it can flip around and move around so it's all 109.5 degrees, we have 0 ring strain. It combusts as if it were that many CH2 groups in a linear chain. So that's our magic number. That's why we work with cyclohexanes, because it has 0 ring strain. Okay. Now, as you grow up, you think, well, you know, we have a bigger ring, we should have less ring strain. Well, actually, it turns out conformationally, because of the different ways that they have, it's hard to get them all at 109.5 degrees because of the way the rings are arranged. You're starting to get things that groups on the sides are starting to interact with each other. They can't get to that full 109 on all the angles, and therefore our ring strain actually increases as we go up. Okay, so our magic, you know, Goldilocks, you know, cyclohexane here is 6 carbons, and that's why we use cyclohexane so much in our descriptions. Okay, questions on ring strain or even the stability of the thing based on the heat of combustion?
Can you go over one more time, sorry, about why after 6 the strain increases again?
Okay, so in that case here, because you can get a perfect orientation where every single carbon has that 109 degrees apart, adding that extra carbon, that CH2 in there, now puts a little tweak, tweaks one of those carbons out. And so we're starting to see the hydrogens start to butt up against each other again. There's no way for it to configure itself such that everything is at 109.3 and in a perfectly staggered configuration. So there's going to be some that are starting to get in where we're starting to have groups that are starting to impinge each other because of that. That extra just CH2 is has to go somewhere, and it's not symmetrical, and so you end up with hydrogen starting to become more butted up against each other, which leads to the ring strain. And it happens more and more as you get to higher and higher numbers.
Okay, that makes sense. Thank you.
And I think I have a couple drawings that I can show you that. Okay, so cyclohexane is our great thing. So by heat of combustion, if we look at just the CH2s versus the heat liberated, it is our most stable alkane. It has the least amount of torsional strain and angle strain. And it's because when we're going to draw a Newman projection, we're going to see that we don't have any eclipsing hydrogens on any adjacent carbons, right? So when we can get to that full, you know, staggered configuration, we're going to see that has less potential energy. Now, any bond angle less than 109 degrees adds strain to the system. So let's look at this least stable one right here, the cyclopropane. Number one, all of those hydrogens are eclipsed, and we have really tiny angles of 60 degrees. So we have all those hydrogens in the clip adding to the energy. We have the, sorry, that 60-degree angle adding to the energy, making it the least stable system we have. Still, we can still make it, but it's not very stable. Okay. So let's look at cyclohexane and what different configurations it can have. So we have 3 configurations are the primary ones. I'm sorry, 2 configurations of the primary ones, the chair and the boat. This is what we call the chair configuration. And if you look at it, if you redraw it kind of little lengthy outy here, it looks like a chair. So we have the back of the chair, the seat of the chair, and then the foot of the chair. Okay, so that's why we call it the chair conformation. And in the chair conformation, all of the atoms are staggered in that configuration. So when we do our Newman projection of this, we're going to see all staggered configurations. However, if you were to take our chair and start pulling this up, you know, with its because we can rotate on sigma bonds, it will be able to flip up into a configuration called the half chair. This is a huge energy barrier because we're starting to eclipse all of these hydrogens that we're going to see here are going to be eclipsed, and so it's a high energy conformation. That kind of cascades down into a twist boat where we only have half as many eclipsed hydrogens until we get to the boat. In the boat, we have hydrogens that are sticking up, hydrogens that are sticking out here, and we have some eclipsed hydrogens over here. So it's higher in energy than our chair, but it's still one of those configurations we'll be able to see. And then, of course, we keep flipping it over and we get all the way back to the opposite chair. So these are the different configurations, and showing you that, notice these are much higher energy barriers than if we were just rotating two methyl groups, because we have to move all of those 6 atoms in the carbon chain, all of those CH2s all at the same time. So the additive effect of all of those things, you know, eclipsing, is very pronounced in this, with this a very high energy barrier. Okay, so let's look at a Newman projection and talk about the staggered configuration we have. Okay, so in the case of our chair configuration, if we draw a Newman projection down, let's see, that's on the 2, 3, we're going to look down this bond right here and this bond right here on our Newman projection, which puts our 1 carbon in the front. So this is our, we're going to look at it in this direction here. So I'm going to put my eye over here, and that makes this 4 carbon here in the back. Okay, so this is our 4 carbon in the back, this is our 1 carbon in the front, and we're going to look down those 2 other bonds. When we do that, we see that, I'm going to go ahead and circle this. Do you have a question? There's a mic on. So, Nardos, you have a question? No? Okay. All right. No question. All right. So then, we're going to have this carbon is our front one, and this carbon is our back one. And now we're going to take a look. So just like before, the 2 carbons closest to us are going to have the lines that intersect in the middle. And the carbon behind is going to be the ring with those hydrogens or carbons that are attached to it behind. So now we have our Newman projection. Notice that every single atom here is staggered. Okay, we do have a Gaussian interaction between these 2 carbons in our ring, but other than that, everything else is staggered. Okay, so everything is at 109.5 degrees, and there's no angle strain. And because all the hydrogens and carbons are perfectly staggered, we have no torsional strain either. Okay, that's why the chair conformation is a low energy position. Okay. Now, we have a new thing to talk about, is the nomenclature of what types of hydrogens we have. So if we were to draw like a planet and had an axis right here, and our planet was rotating around this axis here, we have 2 kinds of carbons. We have the, hydrogens. Hydrogens that are aligned with that axis, and carbons that would be on the equator of that planet created by that axis, okay? So we have what we call axial hydrogens, which are the ones that are going to be pointing straight up and straight down. You can imagine if you had a model, those would be the legs sitting on the table, and there'd be 3 poles sticking out. And then all the ones that are around the outside here are what we call equatorial positions, because they go all the way around the outside of that molecule. Okay, so we have a nice stable configuration because it's perfectly staggered, but we have 2 types of hydrogens. We have the axial hydrogens here are closer together than the equatorial hydrogens. And so that's going to play a role in other conformations available to us in the cyclohexanes. Okay, let's do that and that. All right. So let's look at that in the boat configuration. And it's, of course, less stable, but let me show you why. When we draw our Newman projection for this, again, we're going to draw it down. We're actually going to draw it from this direction here because the 2's in the front and the 1's in the back, and the 4's in the front and the 1's in the back. So we're going to draw our Newman projection looking down these two axes here. And what we see is in this state here, we have actually eclipsed bonds. All of our systems are eclipsed, okay? So in that case, we have a higher energy system because it's eclipsed. In our chair conformation, we had completely staggered, okay? And only one gauche interaction with the methyl groups. Now, when we have the boat configuration, we actually have another energy barrier to us, and that's what we call these flagpole hydrogens. So if we had the boats, you have the ends of the boats, and you have two flags on there, those two hydrogens are the closest together of any of the hydrogens in the system. And so they're going to push each other apart, and that gives rise to additional energy required to make it do this. Not only do we have all of our eclipsed things right here, but now we have, let's see, the hydrogen on the 3. Oh, that's interesting. The hydrogen that would be on the 3 and the hydrogen that would be on the 6 down here are butting up against each other, giving us additional strain. Now, additional conformational strain. Notice that all the angles are still 109, but the fact that we have those eclipsed interactions is what's giving us our additional energy. Okay, so I'm going to show you how to draw the chair conformation and make it really, really easy. Okay, so you got to practice this a little bit to do, but you know, it should be easy after you practice it a couple times. So I'm going to do that, and that's the last thing we're going to do today. So the idea here is that when you draw a chair, you want to start with your two parallel bonds, and you have to think of one's going to be in front of the other because it's a three-dimensional object. Okay. Then the next thing you want to do is you want to draw a bird mouth on one side of it, and then a bird mouth in the other direction on the other side of it. By doing this, you've now got all of your parallel lines. Notice that these are now parallel with that. These are parallel with those, and the red ones were parallel to start with. Okay, that gives us a great place to start. Now we have to add hydrogens. So it's best to add the axial hydrogens first because you can go up, 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 down, 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 and then draw in the equatorials around the outside. Notice these are going to be kind of pointing up and down, alternating up and down. So our equatorial, where's my, our equatorial, I'm circling in red here. Notice how they're all the way around the outside. And our axials, which I'm going to circle in blue here, all kind of stick up in the same direction. All of these axials stick down in the same direction. Okay. Now, when you draw it this way, it makes it easy to see which groups are interacting with which groups. You'll see that the hydrogens on the axial hydrogens are interacting with the axial hydrogens. And the equatorial hydrogens are having a minimal interaction, but they only react with the equatorial hydrogens. Okay. So if you try to draw it with weird bond angles, you won't be able to see the relationship between the substituent and the ring itself. So try to do it that way. And again, this is an easy step-by-step way where you do all your axials, then fill in the equatorials as you go. Okay, questions on drawing a chair conformation? Okay, I want you to practice that a couple times because we're going to draw a lot of chair conformations next time. Okay, so I'm going to go ahead, and it's 9:19. I'm going to go ahead and stop sharing and stop recording and answer any questions you have.